How does the architecture of a transformer model facilitate parallel processing, and what are the implications for training efficiency? Now, transformer architecture was introduced by Vaswani and team in about 2017. It was the paper from Google Mind or DeepMind called "Attention is All You Need." And that fundamentally, in many ways, reshaped deep learning by eliminating recurrence and enabling essentially parallel computation over sequences. This was a critical departure from architectures like RNNs and LSTMs. There was an underlying bottleneck that's important to understand. Recurrence bottlenecks in RNNs, which were sort of the traditional sequence models, they process inputs and they process tokens sequentially, maintaining hidden state from one step, or what's called one time step, to the next. What this unfortunately did, it limited parallelism, as each time step must wait for the previous one. So it slows down training, especially long sequences. It creates optimization challenges, example, vanishing or exploding gradients. So the question that's asked is how transformers enable parallel processing. Well, transformers replace recurrence with self-attention, allowing the model to process all tokens in a sequence simultaneously. Positional encoding decouples order from computation, since transformers lack recurrence, and they encode the position of tokens using positional embeddings or sine or cosine or learns. And this allows all tokens to be processed at once while still retaining order information, and that is very important. Self-attention is fully parallelizable. The core operation, which is a self-attention operation, computes attention scores between every pair of tokens in a sequence, and they use a particular formula that we'll sort of put up on the screen as well. And this is essentially a matrix-to-matrix operation. And what this enabled us to do is enabled us to apply GPU-accelerated parallel computation using batch matrix multiplication. There was certainly no dependency on token order for forward computation, and every token can be updated simultaneously. Feed-forward layers are token-wise, certainly after attention, and each token passes independently through a shared position-wise feed-forward network. Now, again, this allows for full vectorized processing across tokens, a sharp contrast to the temporal dependence that existed in recurrent neural networks. Multi-head attention is also parallelizable across heads. The model uses multiple attention, what are called heads, to learn different aspects of relationships in parallel, and these are independently computed. They are often concatenated and linearly projected. And this structure is inherently friendly to data parallel and model parallel execution. The third area is implications for training efficiency. Now, the architectural features of transformers translate into major gains in both training speed as well as scalability. You get certainly better GPU utilization. So, for example, matrix multiplications for QKV and the attention output can be batched efficiently across the entire sequence. And this leads to high flop utilization on GPUs and TPUs, as operations are now better aligned with modern hardware accelerators. There's also a lower wall clock time per epoch. So RNNs require O(n) sequential operations, whereas transformers compute in O(1) per layer all tokens. This is a huge gain in throughput. It enables faster convergence and experimentation on large data sets. There's also scalability to long sequences with certain caveats. So while naive self-attention scales quadratically with sequence length, O(n) to the power of 2, efficient transformer variants, example, longformer, performer, flash attention, reduce this to sort of linear or sub-quadratic time, and that again enhances scalability. Now, one additional thing it does, it enables pre-training at scale. The ability to train on massive batches of sequences is one of the key enablers of large language models like GPT, BERT, T5, and Llama. Now, combined with data and model parallelism via frameworks like DeepSeed or Megatron LM, training can now be distributed across thousands of GPUs efficiently. So, in summary, the transformers architecture is intentionally designed to remove the sequential bottleneck of earlier models by using parallel self-retention instead of recurrence, by encoding position explicitly instead of relying on stepwise state updates, and by leveraging matrix operations aligned with GPU and TPU hardware. So, in a nutshell, transformers make it possible to scale AI models horizontally and vertically in truly unprecedented ways. And this is the foundation for today's frontier models, not just in NLP, but increasingly in vision, audio, and even multimodal systems.